If you take an engine apart, weigh every single gear and piston, and put it all back together, the rebuilt engine will weigh exactly the same as its scattered parts. That is how we expect physical reality to work. But at the atomic level, those expectations fail. Take an atom of oxygen-16, built from exactly 8 protons and 8 neutrons. Measured in their free, unbound state, these 16 particles combine to precisely 16.12744 atomic mass units. However, an intact oxygen nucleus measures just 15.99053 units. The assembled nucleus actually weighs less than its scattered parts. There is a gap of 0.13691 units. A measurable fraction of the atom's mass has vanished from the scale during assembly. Physicists call this exact numerical discrepancy the mass defect. The standard arithmetic of physical objects no longer applies here. In the nucleus, parts lose physical mass simply by binding together. Albert Einstein's mass-energy equivalence provides the solution to this exchange. Mass and energy are two versions of the same thing. Protons are positively charged, which means they violently repel each other. Forcing them into a tiny nuclear space requires an immense amount of glue. The missing mass was converted into the raw energy required to bind the atom together. This converted energy is known as binding energy. To calculate it, you multiply the mass defect by the speed of light squared. In practical terms, 1 unit of atomic mass translates to 931.5 mega-electron volts. For our oxygen-16 atom, that missing fraction of mass becomes a massive 127.5 mega-electron volts of binding energy. But comparing total energy across different elements is misleading. A heavy element like uranium will naturally have a higher total binding energy than oxygen simply because it contains more protons and neutrons. To create a fair comparison, we calculate the binding energy per nucleon. We divide that total energy by the number of particles inside the nucleus. This isolates the average energy holding each individual particle in place. It is the metric physicists use to measure the true stability of any atom. The place coordinate on this curve dictates its stability, its behavior, and its potential for nuclear reaction. So why does this graph plateau? Why doesn't the binding energy just keep climbing as you add more particles to a nucleus? It comes down to the saturation property. The strong nuclear force is short-ranged. A nucleon only feels the attractive pull of the neighbors it is physically touching. It is unaffected by the particles on the far side of a large nucleus. Because of this limitation, elements on the slopes of the graph are constantly driven to move up the curve, seeking the stability of the middle region. Massive elements on the right achieve this by splitting into 2 middle mass fragments. This nuclear fission releases their excess mass as energy. On the left, light elements violently collide and merge to form a single heavier nucleus. This process of fusion releases a blinding shockwave of energy as the new nucleus becomes more tightly bound. The mass defect in an oxygen atom is the exact mechanism fueling the stars, defining the energy yield of every nuclear reaction in the universe.